Officials in China have begun load testing what will become the world's tallest bridge. The structure will reduce travel time in the Chinese city from 2 hours to 1 minute.
They said it could not be done. China did it anyway. 600 meters above a raging river, engineers suspended an entire highway in midair using cables strong enough to lift a warship. American scientists watched the footage in stunned silence. Some called it impossible. Others called it the most terrifying engineering achievement in human history.
But that doesn't mean it's always been easy to get to. Historically, Guizhou has been something of an isolated island, and while accessing it was difficult, moving around it was even harder. And that's why the Chinese government are spending billions to try and better connect this region with the rest of the country.
A canyon so deep it swallows sound. A bridge so high it punches through the clouds. $300 million. 4 years. One structure that made the rest of the world stop and stare. What you are about to see will change how you see engineering forever. Deep in the heart of Guizhou Province in southern China, the land breaks apart. The ground simply stops, and in its place sits one of the most dramatic natural features in the country, the Wujiang Canyon. The gorge drops hundreds of meters straight down, carved over millions of years by the Wujiang River, winding through the limestone karst below. For the communities on either side, this canyon has always meant distance. A journey that should take a few minutes instead takes the better part of 2 hours, winding along mountain roads that follow the terrain rather than cutting through it. For decades, that was simply the reality of living in this part of China. Then engineers decided to change it. The proposal was straightforward in concept and extraordinarily complex in execution. Build a bridge across the canyon. Not just any bridge, but a suspension bridge that would hold the record for the highest bridge in the world, with its deck sitting roughly 625 meters above the river below. The total span between the two anchor points stretches to around 1,420 meters. To put that into perspective, that is longer than many of the most well-known bridges in Europe and North America. And it sits not over a calm estuary or a flat river plain, but across a jagged mountain gorge at high altitude, where the wind behaves in ways that flat terrain engineers rarely have to think about. Before any machinery moved, before a single worker set foot on the canyon rim, the project existed entirely on paper and in computer models. The planning phase for a structure of this scale is not a formality. It is arguably the most important part of the entire build. Engineers and surveyors spent considerable time studying the canyon itself, mapping its walls, sampling its rock, and feeding data into simulation software to understand how the structure would behave under every condition they could anticipate. Wind loads, seismic activity, temperature fluctuations, the weight of traffic, the tension of the cables, all of it was modeled and tested before construction began. One of the first tools deployed during this survey phase was aerial drone technology. Fleets of drones were sent out to scan the limestone cliff faces on both sides of the canyon, capturing detailed three-dimensional maps of the rock. The goal was to identify the most stable anchor points, locations where the rock was dense enough and structurally reliable enough to hold the enormous forces that a bridge of this size would generate. Suspension bridges work by transferring the weight of the deck and the traffic it carries up through vertical hangers, along the main cables and ultimately down into anchor blocks at each end of the bridge. Those anchor blocks are only as good as the ground they sit in. If the rock is fractured, porous, or otherwise compromised, the entire system is at risk. The drone surveys helped engineers avoid those weak zones and identify where the ground could be trusted. With the survey data collected and the engineering plans finalized, ground preparation began. The first work was not about building upward, it was about cutting in. Access roads had to be carved into the cliff sides to allow heavy machinery to reach the construction zones. In terrain like this, that is no small task. Excavators and drilling equipment had to be moved to positions that were in some cases barely accessible. Workers established routes along the canyon edge, cutting into the rock where necessary to create stable platforms for the equipment that would follow. The anchor blocks came first. In a suspension bridge, the main cables do not simply attach to the towers and stop there. They continue past the towers and anchor into massive concrete structures buried in the ground. These gravity anchors, as they are known, are designed to resist the horizontal pull of the cables through sheer weight and their bond with the surrounding rock. At the Wujiang Grand Canyon Bridge, these anchors had to be capable of holding an almost unimaginable amount of tension. The cables they would eventually hold are among the heaviest ever used in bridge construction. To build them, crews excavated deep into the rock on both sides of the canyon. Steel reinforcement bars, known as rebar, were arranged inside the excavated chambers in dense, interlocking patterns. The tying of this rebar was done largely by hand, a painstaking process given the sheer volume of steel involved. Thousands of individual connections were made, each one contributing to the overall integrity of the structure. Once the steel framework was in place, concrete was poured in a continuous process. Stopping and starting a pour of this kind can create weak joints within the finished block, so the concrete flowed without interruption until each anchor was complete. During the pour, workers used vibrating equipment to remove air pockets from the concrete. This step matters more than it might appear. Air pockets left inside a concrete structure create voids where cracks can form under load. In a standard building, a small void might cause a minor problem over time. In an anchor block holding the main cables of the world's highest bridge, it represents a potential failure point that engineers simply cannot accept. Once the concrete cured and hardened, it effectively became artificial rock, bonded to the natural stone around it and capable of resisting the forces the bridge would place on it for decades to come. Set into the face of each anchor block were the cable anchor bolts. These are the physical connection points where the main suspension cables would eventually terminate. Each bolt was installed to precise engineering tolerances and torque to specific values, verified by calibrated equipment. There is no informal approach to this kind of work. The specifications exist because the calculations behind them are exact, and deviation from those specifications introduces variables that the original calculations did not account for. While the anchor blocks were being completed, the foundations for the main towers were being prepared at the canyon rim on both sides. The towers of a suspension bridge are the most visible elements of the structure, but their stability depends entirely on what is beneath them. At this site, the tower foundations had to contend with the additional challenge of high-altitude winds. Wind loads at elevation are considerably higher than at sea level, and the canyon itself creates channeling effects that can concentrate and accelerate wind in unpredictable ways. To address this, the foundation design called for steel reinforcement cages to be sunk deep into the bedrock, creating roots for the towers that would resist both vertical loads and the lateral forces generated by wind. Concrete pump trucks with extended booms reach down into the foundation excavations, delivering concrete to depths that would have been difficult to reach any other way. The curing process for foundations at altitude required careful temperature monitoring. Concrete that cures too quickly in cold conditions or too slowly in unusual humidity can develop internal stresses that reduce its long-term strength. Workers and engineers tracked the conditions closely throughout, adjusting where necessary to ensure the foundations met the required standards. By the time the foundation and anchor work was complete, months had passed. Nothing visible had risen above the canyon rim. To a passing observer, the site might have looked like a large and busy excavation project with no obvious end product in sight. But the work done in this phase was the work that made everything else possible. The towers, the cables, the deck, the road surface, the glass walkways and the lighting, all of it would eventually rest on decisions made and work carried out during these early weeks and months. The ground had been prepared. The next phase could begin. With the foundations set deep into the bedrock on both sides of the canyon, the character of the construction site changed entirely. The excavation equipment moved out and a different kind of machinery took its place. Tower cranes were assembled at each foundation platform, their latticed arms rising above the canyon rim. These cranes would not build the towers directly, but they would supply the materials and equipment needed for the teams working on them. The towers themselves would be built using a method called hydraulic climbing formwork, a system that has become standard on major concrete tower construction projects around the world. It is methodical, repetitive, and effective. The process works in stages. A section of formwork, essentially a mold for the concrete, is fixed in position around the growing tower. Concrete is poured into the mold and left to cure. Once it has reached sufficient strength, the formwork is hydraulically jacked upward to the next position, and the process repeats. Pour, cure, climb. Pour, cure, climb. It sounds simple, and in principle it is. But at the scale of the Huajiang Grand Canyon Bridge towers, and at an altitude where the weather is unpredictable and the wind rarely stops, each cycle requires careful management. The concrete mix has to be adjusted for temperature and humidity. The formwork has to be checked for alignment after every climb. The growing tower has to be monitored continuously for any deviation from vertical. The towers at Huajiang are not simple vertical columns. They are H-shaped structures consisting of two legs connected by crossbeams at intervals along their height. The legs rise in parallel, each one following the same climbing cycle, but they have to remain precisely coordinated with each other throughout the process. If one leg pulls ahead of the other, even by a small margin, the crossbeams that lock them together cannot be installed correctly, and the structural integrity of the tower is compromised. Survey teams checked the geometry of the towers at every stage, using precision instruments to verify that each leg was rising true and that the spacing between them remained consistent with the engineering drawings. The crossbeams themselves represent a significant construction challenge. They are not small connecting pieces. They are substantial structural elements that have to be installed at height in conditions that often include strong winds and fixed to both tower legs simultaneously. Workers operating at these elevations are not doing so in the controlled environment of a workshop. They are on exposed platforms hundreds of meters above the canyon floor, where the wind can change direction without warning and the temperature can drop sharply in the space of an hour. Every lift of every component is planned in advance. Load weights are calculated, crane capacities are verified, and the weather window for each major lift is assessed before work begins. As the towers grew, the engineering principle behind their design became increasingly relevant. Suspension bridge towers are not designed to be rigid in the way that a concrete building column is rigid. They are designed to flex. The loads they carry are dynamic rather than static. Wind pressure changes constantly, temperature causes the steel and concrete to expand and contract, and the tension in the set. Cable shifts as traffic moves across the deck. A tower that cannot accommodate these movements would accumulate stress at its base until something gave way. The towers at Huajiang were designed with this in mind, their proportions and material properties calculated to allow a degree of movement while maintaining full structural integrity under all anticipated loading conditions. The saddles installed at the top of each tower are a component that many people outside of bridge engineering would not think about, but they are critical to the function of the entire structure. A saddle is essentially a curved steel cradle that sits at the tower peak and guides the main suspension cable over the top of the tower. The cable does not attach to the tower at this point. It passes over the saddle and continues down to the anchor block. The saddle has to be positioned with exceptional accuracy because its location determines the geometry of the cable on both sides of the tower, and the cable geometry in turn determines the profile of the finished bridge deck. If the saddle is out of position, every subsequent element of the bridge is affected. With both towers standing at their full height and the saddles installed, the site entered what the narration of the original footage describes as the most dangerous phase of the entire project. The two towers stand on opposite sides of a canyon that is, at this point, still a completely open void. There is no platform, no temporary structure, no way to walk from one side to the other. The first connection between the two sides has to be made through the air. The solution used at Huajiang and on major suspension bridges elsewhere in the world involves a drone. A relatively lightweight, unmanned aircraft carries a thin pilot rope across the canyon from one tower to the other. The rope is not structural. It cannot carry any meaningful load. Its only purpose is to establish a physical link between the two sides so that heavier lines can follow. Once the pilot rope is in place, it is used to pull across a heavier cable, which is then used to pull across a heavier one still. Each successive line increases the load capacity of the connection, and through a series of these steps, the system eventually has enough strength to support the installation of the aerial catwalk. The catwalk is not a finished walkway in any aesthetic sense. It is a functional working platform, a narrow, mesh-floored path suspended in the air between the two towers, running the full length of the bridge span. It sways in the wind. It offers no shelter. The drop on either side is measured in hundreds of meters. For the workers who use it daily during the cable spinning phase, it is simply the route between where they start their shift and where the work needs to happen. It takes a particular kind of person to walk that path without hesitation, and the teams on this project did exactly that, day after day. Cable spinning is the process by which the main suspension cables are formed. The cables on a bridge of this scale are not manufactured elsewhere and delivered to site. They are built in place, wire by wire. A spinning wheel travels back and forth along the catwalk, carrying individual steel wires from one anchor block to the other. On each pass, it lays another wire alongside those already in place. This process repeats thousands of times. Workers stationed along the catwalk monitor the wires as they are laid, checking tension and alignment, and organizing the accumulating bundle into neat, ordered strands. The organization of the wires within the cable matters because an evenly distributed bundle, with each wire carrying its share of the load, is significantly stronger than a randomly arranged one where some wires take more tension than others. As the cable grows, the transformation from a thin collection of wires into a massive structural element is gradual but striking. What begins as a cluster no thicker than a person's arm eventually becomes a cable with a diameter of over a meter, dense with thousands of individual high-strength steel wires running parallel to each other along its entire length. A hydraulic compactor is used to squeeze the bundle into a circular cross-section, removing the air gaps between wires and creating a tighter, more efficient structure. The finished cable is then wrapped in a protective outer layer and sealed against moisture and corrosion. The steel used in these wires is specifically engineered for this application, with a tensile strength that allows a single completed cable to carry loads that are difficult to comprehend in everyday terms. The cables at Huajiang are capable of supporting forces equivalent to the weight of a large naval vessel. Once both main cables were complete and secured at their anchor points on each side, the next stage was to install the cable clamps. These are steel fittings attached to the main cable at precise, pre-calculated intervals along its length. Each clamp has a connection point for a vertical hanger, and it is the hangers that will eventually carry the weight of the bridge deck. The positioning of every clamp is determined by the final geometry of the deck. If a clamp is even slightly out of position, the hanger attached to it will not meet the deck at the right angle, which affects the load distribution across that section of the bridge. Survey teams worked along the catwalk to verify each clamp placement before it was fixed in position. With the clamps installed, the hangers were attached and dropped downward from the main cable, hanging free in the air above the canyon. They would remain this way, swaying in the wind at altitude until the deck segments arrived to give them something to connect to. The cables were complete, the towers were standing. The anchor blocks were buried in the rock. Everything was in place. The skeleton of the bridge existed. What it needed now was the surface that people and vehicles would actually use, the deck that would turn this engineering framework into a road. The deck of a suspension bridge is not a single continuous piece of steel lowered into place in one movement. It is built section by section, segment by segment, each piece lifted from below and connected to the hangers that have been waiting for it. At the Wujiang Grand Canyon Bridge, the deck was constructed using a steel truss girder design. This is a deliberate engineering choice for a site like this one. A solid web girder, the kind used on many urban bridges, acts like a sail in strong wind, catching the air and generating forces that the structure has to resist. A truss design, by contrast, allows wind to pass through the open framework, significantly reducing the lateral loads on the towers and cables. In a mountain canyon where wind is a constant and sometimes severe presence, that difference matters enormously. The individual deck segments were assembled on the ground, away from the canyon edge, before being transported to the lifting points. Pre-assembling the segments at ground level rather than at height is standard practice on projects like this. It is safer, faster, and allows for more precise quality control. Workers can move around the segment freely, check every weld, verify every dimension, and make corrections before the piece goes anywhere near the canyon. Once a segment has been lifted to its final position, hundreds of meters above the river, making changes becomes exponentially more difficult and dangerous. The lifting system used for the deck segments was the cable crane, a type of crane that runs along the main suspension cables themselves. Unlike a conventional tower crane that rotates around a fixed mast, a cable crane travels horizontally along the cable span, allowing it to position itself directly above any point along the length of the bridge. This is essential for a deck installation of this kind, where segments need to be lifted and placed at locations spread across more than a kilometer of span. The cable cranes at Huajiang were tested with dead weights before any steel deck segment was ever attached. Sensors monitored the tension in the crane cables during these tests. verifying that the system was performing within the expected parameters before the real lifts began. The installation sequence for the deck segments followed a specific pattern. Rather than starting at one end and working toward the other, the teams worked from multiple points simultaneously, lifting segments from the center of the span outward and from the ends of the span inward. This approach keeps the load on the main cables and towers as balanced as possible throughout the installation process. A suspension bridge in the middle of deck installation is in a state of constantly changing load distribution, and maintaining symmetry reduces the stress concentrations that could develop if one side of the bridge were significantly heavier than the other at any given time. As each segment arrived at the suspension level, workers guided it into alignment with the hangers on both sides and pinned it into position. The connections were made temporarily at first, allowing for minor adjustments before the final welding took place. GPS equipment was used throughout this phase to verify the position of each segment to millimeter accuracy. The deck of a bridge this size has to follow a precise geometric profile, not perfectly flat, but deliberately curved in a way that accounts for the deflection that will occur once the bridge is carrying traffic. Getting that profile right during construction requires constant measurement and adjustment. The welding of the deck segments into a continuous structure is the moment the bridge truly becomes one piece. Each joint between segments was welded by certified welders working to strict procedural standards, with the finished welds inspected and tested before the next segment was brought up. Ultrasonic testing was used to check for internal defects in the welds without cutting into them. This is standard practice on critical structural steel, and at a bridge of this significance, every joint was treated as critical. The final segment to be installed was the closure segment, the piece that fills the last remaining gap and completes the deck. It is referred to in engineering circles as the keystone of the bridge, and its installation is one of the more technically demanding steps in the entire process. The geometry of the closure segment has to match both sides of the gap precisely, because at this point there is no room for adjustment. The pieces either fit or they do not. At Huajiang, they fit. With the structural deck complete, the finishing work began. A layer of reinforced concrete was poured across the steel truss to form the base of the road surface. This layer adds weight and stiffness to the deck, helping to dampen vibrations and providing a stable foundation for the asphalt above it. The asphalt itself was laid in a final pass, creating a smooth, durable driving surface designed to handle heavy traffic loads for decades without significant deterioration. The temporary catwalks that had served as the construction highway throughout the cable spinning and deck installation phases were removed once they were no longer needed. Anti-corrosion paint was applied to the exposed steel elements of the bridge, a protective measure that will need to be maintained over the life of the structure, but that begins with a thorough first application at the completion of construction. Safety barriers were installed along both edges of the carriageway, and glass-floored walkways were added on the outer edges for visitors, offering views straight down to the river more than 600 meters below. Lighting was installed along the full length of the bridge, transforming it at night into something that reads less like infrastructure and more like a structure built to be looked at. The lane markings were painted, the signage was put in place, and in September 2025, the Wujiang Grand Canyon Bridge was officially opened. A final load test was carried out before the opening to confirm that the bridge performed in line with the engineering predictions. It did. The practical impact of the bridge is immediate and significant. The 2-hour road journey that residents on either side of the canyon had made for years is now a crossing that takes roughly 2 minutes. For communities that have historically been cut off from each other and from the wider regional economy by the canyon, that change is not a minor convenience. It affects how people work, where they can access services, how goods move through the area, and what economic opportunities become viable that were not before. The bridge has also drawn attention as a destination in its own right. The glass walkways, the bungee jump platform, and the sheer visual spectacle of a road suspended more than 600 yards, meters above a river, have made it a point of interest for visitors. That kind of tourism has its own economic value for the surrounding region, bringing people and spending to an area that previously had little reason to attract either. What the Wujiang Grand Canyon Bridge represents, beyond its immediate practical function, is a demonstration of what modern civil engineering is capable of when the problem is difficult enough to require every available tool and technique. The drone surveys, the hydraulic climbing formwork, the cable spinning, the GPS-guided deck installation, the embedded structural monitoring systems that will track the bridge's health for the rest of its working life, none of these are experimental technologies. They are proven methods, applied here at a scale and in conditions that pushed each one close to its limits. The result is a structure that will stand as one of the more remarkable pieces of infrastructure built anywhere in the world in recent years.